Thank you very much.
Thank you. So, is Vasily Galfraev ready?
Let's see, can you hear me?
Yeah, very good.
Nice. So, it's, can you see my presentation?
Yes, we see.
Okay, so then I move a pointer. Can you see my pointer moving in the middle of the screen? No, okay. Okay, that's, okay, so can I start?
Oh, yes, of course.
Okay, thank you. So good morning to those who are in the West and good afternoon for those who are in the East. And I would like first to thank Sergey for giving me an opportunity to speak about my recent results here. And I'm very grateful to Bernard, who provided a very nice introduction to the technical part, which will be hidden deep behind the bonnet in my talk. And today I'm going to tell you a small story about properties of solitons in a model which comes from the water waves, so it will be just one particular equation. And the object which is studied in this equation is called an embedded soliton. And I feel that I need to explain what this is. So a soliton is a localized wave which moves with a constant speed in one direction. And we will assume that the space is one-dimensional. And then it was realized somewhere in the end of the 90s that such localized solution can coexist with small amplitude linear waves which moves at the same speed. And one such example, so the solitons of this type, so the usual solitons which have a bell shape, which consists with a small linear wave, are called embedded solitons. And embedded refers to the relation of these solitons with a spectrum of linear waves. So the first example of that type was given by Champnitz and Groves in '97. And they studied the partial differential equation, which was derived from early equation from fluids, and it doesn't matter how it appeared. But what is important that, okay, this equation is of order, let's see. Okay, so this equation is of order 5. So you note that there is a derivative here, which adds to the 4 derivatives which are in the x variable in this part. And this equation depends on many parameters, but 2 parameters b and a are important here. If we look on the small waves which can propagate in this equation, we can substitute instead of u some constant a, the amplitude times the exponential, which describes the usual harmonic wave which moves in the space with a phase velocity c. And then it's very easy to establish that such solution can exist only if the frequency omega is related to the wave number k by the dispersion relation, which takes the form that omega is equal to some polynomial of order 5 in k. Or we can eliminate omega and write it in terms of the wave number k and c. So we see here an equation which is a biquadratic equation with respect to k. And if this equation has real solution, we have a sinusoidal wave. And if k is a non-real number, the local small amplitude solutions are unstable and they can grow or decay in time. And looking on this quadratic equation, we see that there is a simple bifurcation in this equation, then c is equal to a. So when the velocity is equal to the constant in the parameter. And this, when C is equal to A exactly, one solution is a double zero, and another solution could be either real or complex depending on the sign of B. And what we observe at the transition when C crosses A is that on one side we get small real K, and that means that in the equation there are waves which are very, very long, and they become longer as C approaches to A. And on the other side, when C is larger than A, the solutions becomes unstable, so they grows or decays exponentially. And that opens a possibility for existence of soliton solution if the branch which decays on the left coincides with a branch which decays on the right. And that happens that if we count dimensions in this model, then solitons may exist, but they don't exist generically. What Champnitz and Grove discovered, that if you draw on the plane of the parameters A and B, the points which correspond to existence of soliton waves, you will see lines. One line, the first one, is actually explicitly computable. So it's very easy to compute this line. It's a parabola with explicit expression. But the rest of this picture was computed numerically. And you see that these lines have two properties. So they connect a point which is on the positive axis here, and they go in a parabola-like shape till they reach the negative axis. And here you see that these lines do not reach the axis. And the reason is that it's not the problem with the original equation. The problem is with the numerical schemes. So something which is closely related to what Bernal told in his talk appears there. So there are some exponentially small phenomena there which are responsible for existence of solitary waves. And that makes computations with ordinary precision impossible. So Champnitz and Groves had to leave the continuation and parameter very close to this axis. And one thing which they also noted, that although they computed only 4 lines, which corresponds to existence of solitary solutions, they conjectures that there is a countable number of such lines on the parameter planes, which goes to infinity in all directions. And the goal of my talk is to explain why there are infinitely many such branches and how it's related to the bifurcation theory and how it relates to a singular perturbation theory. So in order to study that problem, we go to the ODE's point of view. And the standard idea in this part of mathematics is to look for the solution of a partial differential equation in the form of a traveling wave. So a function u depends on x minus ct, which means that we are looking for a solution of a partial differential equation which has constant shape, which moves with constant speed c. And from the ODE points of view, so the function u now becomes a solution of an ordinary differential equation. And a soliton means a localized solution which converges both at plus infinity and the minus infinity to 0. So embedded soliton is a solution to a saddle center. For those who know saddle centers very well, like Lev here, it's in the saddle center, there is a family of Lyapunov orbits which represents a small amplitude harmonic waves which moves at the same speed as the soliton. And then in this setup, there are several methods which can be used in order to detect homoclinic solutions. So the easiest way is in the situation if the equation is integrable, then solitons can be found explicitly or almost explicitly. Then if there are explicitly known solitons, a regular perturbation theory can be applied, so it's like expansion in parameters. In some cases, regular perturbation theory is not applicable and single perturbation theory has to be applied. And we will discuss this point of view a bit later in this talk. And finally, there are solitons which may appear in bifurcations. And at the end, if the equation doesn't look like something which we can solve, numerical methods can be always used. Now let's have a look in more details what of these methods is applicable to the equation we study. So instead of the equation which I wrote at the beginning, I will write a slightly generalized equation. So I am taking the equation which appears from the PDE I showed you at the very beginning, but I replace the coefficients by arbitrary numbers ak, and in total there are 5 coefficients. And it's very easy to see that if u equal to 0 satisfies this equation, and this u equal to 0 corresponds to a saddle center if and only if the product of A0 and A2 is negative. And we will have a deeper look into this situation. So first of all, when we look on this differential equation, they're very important for us, we see that it's a 4th order equation. And looking on this, we can rewrite this equation as a system of 4 equations. And then it will belong to 2 interesting classes. So first of all, this equation is reversible, so it has a time reversing symmetry. And then it's a Hamiltonian system with 2 degrees of freedom. I'm not going to write how to transform this single equation into the form of a Hamiltonian equation because the formulas become more cumbersome and not really helpful for this talk. But what I can immediately notice with this equation that since it's a Hamiltonian system of 2 degrees of freedom, we would be very lucky if we will be able to find solitons or homoclinic solutions for this problem explicitly. Although one case is obvious. If A0 vanishes, then we get an equation of the 2nd order, which is a Hamiltonian system with 1 degree of freedom, which can be solved. But this case is a singular limit. So if we study the equation, which we get by substituting A equal to 0, then we can check by explicit computation that this equation has a solution if a couple of conditions is satisfied. The first one, that A1, A2 is negative, which means that the origin is the saddle. And then there is a number q, which composed of the coefficients. If it's larger than -1/3, then we see a homoclinic solution. The homoclinic solution cannot be written in elementary functions, so I'm not writing it here. So it's computable in quadratures and inversion of an elementary function. Now, then we study an equation like our 4th order nonlinear differential equation. We often do changes over form that we change the scaling of time. Sorry, so here is a misprint. It should be x variable here is missing. So we scale time and the u variable, and we can also multiply the equation by a constant, so that these changes do not change the form of the equation itself. They only change the values of the coefficients. And in order to study the equation, it's very convenient to realize that there are some scaling invariants. So if we make a change of the scales, then the values of q and p remain constant. whatever other scalings with non-zero constants C1, C2, C3. And also there are three signs which are not changed by the scale. That observation allows us to see what kind of equation can we get out of a general equation without actually doing the computations, which is a very convenient thing to do. Although if we try to write a proof, finding the scaling is important because these constants do contribute to the technical part of the consideration. Now, the first observation with the scaling invariance is that this set, the scaling invariance Q and P, form, in certain sense, a full set. So any two equations with the same Q and P, okay, provided this there is a division by A1, A3, so they should be non-zero. So if AK all are non-zero coefficients, then any two equations are equivalent if they have the same P and Qs. So in particular, any equation is equivalent to the equation at the bottom line. So that's exactly the equation which you get from the PDE. So although I wrote a generalization of the equation, actually by scaling you can put it into the form in the original example of the Champnetz and Groves. But we can also do a different thing. We can move A from the first place in front of U to a place in front of the highest derivative. So if we look on the small values of A, so that's the case when we can find, if you look on the second form of the equation, which is at the bottom of the screen, A equal to 0 corresponds to an integrable equation, which may have a soliton. It's equivalent to the equation where A is in front of U, and in this form where A is in front of U, that corresponds to a bifurcation problem. So that's a problem when one of the eigenvalues of a linearized equation converges to 0. So we see that in this problem, a bifurcation problem is equivalent to a singularly perturbed problem. Now, the problem with singular perturbation is that although the truncated equation, this one, is integrable and it has a soliton, it's not guaranteed that if A is a small positive or just a small number, then the soliton will be preserved. There were some works on this area, and I would mention the works by Lombardi, Yoss in the reversible case, and by myself with Lev on Hamiltonian system, which says that if you want to study the problem of existence of an homoclinic solution for small a, which corresponds to the bifurcation in the equation, then if some constant, which is called a Stokes constant, S of B, is non-zero, then the full equation doesn't have a homoclinic solution when this parameter A is small. On the other hand, in the context of exactly the equation which is shown on here on the screen, not in the general setup, Tobis and Pilinovsky noticed that if the constant S depends on the parameter B, and then parameter B changes, it's possible that the function S of B, the Stokes constant, changes the sign. It has a simple zero. And then from this point, there is a line on the plane of parameters such that for every point on this line, the equation has a soliton. And outside of these lines nearby, there are no solitary solutions. Let me discuss a bit what this constant S of B. A full proof of the fact that exactly this constant S of B Stokes constant is important is a matter of, could be a matter of a different presentation. So it's a long and complicated story, and it is related to moving to a complex time, as Bernold explained to all of us in his talk. But now here I would like to show you that what is the definition of this constant. And in the context of our model, the definition is surprisingly simple. So it comes from the equation which is obtained for A equal to 0. So it comes from an equation which is an equation of the fourth order, which is reversible, which is Hamiltonian. It has 2 degrees of freedom, so it's very likely to be non-integrable. And the origin is a degenerate equilibrium. And we can prove that this equilibrium, although it's not hyperbolic, it has a stable and unstable manifold. So there are functions u plus and u minus, which converge to 0 as x goes to infinity. And then if we plot it in real time, it will look like this. So so that is x, this is u, and then u of x, u minus looks like this, u plus looks like this, and it's very likely that on real they do not meet. So it's very likely that these solutions escape to infinity before they meet each other. Although I haven't checked that, to be completely honest. I suggest that because I know what happens with these solutions when B is large. Then this picture is justified. But we can consider these solutions, u plus and u minus, for complex values of a variable x. And then it can be shown that if x is sufficiently large, somewhere near the imaginary axis, both u plus and u minus are defined for the same values of a variable x. And then the Stokes constant describes the size of the difference between u plus and u minus. So why it's a constant and not a function? So you see that u plus is a function, u minus is a function, so the difference is a function. And we need a short method to define this difference and characterize this difference by a single numbers. So first of all, we need to eliminate the freedom in the definition of a solution u plus and u minus. This u plus and u minus are not defined uniquely because our equation is autonomous. So we can always translate the x variable and obtain another solution from the same solution. So if u plus of x goes to 0, then u plus of x plus c also goes to 0. And this translation freedom is eliminated by fixing the asymptotic behavior of u at infinity. We can look for a solution of the differential equation in the form of a series, power series, and we can substitute this series into the equation and compute the coefficients without caring about convergence of a series, and these coefficients are defined uniquely. And then we can assume that both u plus and u minus are asymptotic to the same series, but one for large x positive, other for large x negative. And that fixes solutions uniquely. Now, let us introduce the eigenvalue, which of a linearization, it's for the future use. And consider the function which is a half sum of u plus and u minus. Then we can do the following. We can use, so when we look on the equation, and we take the difference of two solutions of these equations, Then we can rearrange terms, so we see that delta, which is the difference between u plus and u minus, is an exact solution of this equation. In order to see that, you just need the usual formula for the difference of the squares. So it's a very easy exercise. But when we look on this equation, we see that that is a differential equation for delta, which is of order 4. It contains fourth derivative, second derivative, even the first derivative, and it contains the function uc, the middle function between two solutions, which has the same asymptotic behavior as u plus and u minus, because u plus and u minus have the same asymptotic behavior. Then we can study solutions of this linear equation, assuming that we know the asymptotic expansion of the coefficient uc. And we can establish that this equation of order 4, of course, it has 4 independent solutions. 2 of them oscillates like the linear path of the equation prescribes. 1 solution decays as x to the power minus 3. And 1 solution may grow polynomially of x. Now, we realize that since u plus and u minus have the same asymptotic expansion, their difference decays faster than any powers of x. And consequently, the delta, a solution of a linear differential equation of order 4, which in general is a linear combination of all 4 fundamental solutions of the same equation, actually is proportional to only 1, the one which decays exponentially along the imaginary axis. Okay, this case is if we go upwards, and it's to delta minus if we go downwards. Consequently, there is some constant such that delta of x is equal to this constant s times delta plus. That is the Stokes constant, and that's the constant which is responsible for the fact if u plus and u minus coincide. So if s is equal to 0, then u plus is equal to u minus. If it's not equal to 0, then u plus and u minus are different. And the standard method used based on complex matching can be shown that if s of b is non-zero, so u plus and u minus are different in the complex time, then the stable and unstable solution of the original equation with where the parameter a is not equal to 0 are also different. And the explanation can be of this phenomena can be done using the following argument. Since s of b is a constant, we can study delta of x and delta plus of x for complex values of x, which takes any values. So if you do it on the reals, we see something which is exponentially small, so like the exponentially small splitting of separatrices in the Bernoulli-Stock. But if you look for x near the singularities of the unperturbed separatrix, then their delta grows and delta plus becomes close to each other, and the constant s stays the same. Okay, so I'm not going into that more, but this definition is not probably the most useful one. We can also take a point of view that delta plus behaves by the definition like an exponent with a coefficient 1 plus higher order terms. So the Stokes constant can be defined as a limit. And this formula can be used for numerical computations, and my collaborators did some numerical computations of that, and they managed to compute this constant s with high precision. And there are some methods which can be used in order to accelerate convergence. And I just dropping that, I'm going to But one important thing is I would like to stress what is the geometrical meaning of a Stokes constant. So if a Stokes constant vanishes, then it implies that delta is equal to 0. That implies that u plus of x and u minus of x coincide, and so they form a single analytic functions in the neighborhood of infinity. In this case, the formal series which represent each of the solutions, so these formal series, converge. And this formal series represent a Lorentz series which actually satisfies the differential equation, even if the equation itself is not integrable. Otherwise, if Stokes constant is non-zero, then the formal series diverge, and it can be proved that the divergence is factorial. And that allows a second definition. So we can take the coefficients of a formal series, we can normalize them by factorials, and take the limit for the large values of the coefficient, and that provides us an alternative definition of a Stokes constant, which also gives us a tool for quick computation. So let me drop that. So let me just discuss the main point of why it all was done. So I want to come back to the question which was posed in the original paper by Allen and Groves. It is about what is the reason why there are infinitely many branches of homoclinic orbits in the bifurcation diagram. So what is the reason that the Stokes constant has infinitely many solutions, infinitely many zeros when the parameter b is changes? So let me remind you that the Stokes constant comes from this differential equation. It's very easy to check that this equation is equivalent to another equation. So where b is moved from the place in front of the second derivative to in place of which is in front of the fourth derivative, but with b minus 1. Checking that these two equations are equivalent is easy because both equations have the same scaling invariant. Now we see that for large values of b, the equation is a singular Pertop problem. So you see, we start with a problem of appearance of solitons in a singularly perturbed problem. That is reduced to a problem which is called an inner equation, which defines a Stokes constant. But for large values of b, the inner equation for the Stokes problem again becomes a singularly perturbed equation. Now, what is specific about this singularly perturbed equations? The behavior of solutions to a singularly perturbed systems is dictated by complex singularities of the limits equation. So here the limit equation is when b goes to infinity is an equation of the second order, which looks like this. And this again is a Hamiltonian system with 1 degree of freedom. It can be integrated. The solution is not an elementary function. It's an inverse of an elementary function. So it can be studied. And the point is to study what are the singularities of a separatrix solution, and the position and the properties, the types of the singularities dictates what happens for large b's in the full inner equation. And here we come to something which is somewhat unusual to this theory. As Bernold explained to us, the imaginary part of the singularity of this equation is responsible for the exponential decay. So looking naively on this equation, we could expect that S of b is exponentially small for large b. But in this equation, singularities are located exactly on the real axis. So there is a degeneracy. We get exponentially small phenomena with a zero exponent. And then the properties of unperturbed separatrix is the following essentially, that it can be shown that the U0 is analytic on the whole plane with a cut marked here by the green line, and then it maps the whole plane into inside of these green curve. That dictates that, and that also has a property that there are two singularities, so with the same imaginary path here and here, and that implies that the behavior of the asymptotic will be oscillative. And the latest progress is to prove that the Stokes constant behaves asymptotically something like the equation written here, which decays polynomially in epsilon and behaves like cosine with a shift. And so it has infinitely many changes of sign. In this part, the work is in progress, and I'm finishing here. So it's
1 minute for questions.
Yeah, I've finished. So that is all. So that implies that there would be infinitely many lines with solitons in the original problem.
Very interesting and good result. Have anybody question? One short question. So let us think. Only short question is possible.
Very short is not possible.
So now, what's the asymptotics? What's the asymptotics of the Groves Champneys curves?
So I think that's something which
I mean, I lost track in between how to translate.
Okay, so here is the picture. So the endpoints, the points where these curves reach the axis are zeros of the Stokes constant. So these are computed. So it's also possible to find asymptotics of this part of the curve, but that has not been done.
So these are regular, not oscillatory.
No.
No.
So it's these are they have no oscillatory behavior. So they are regular lines on the plane of the parameters.
Thank you.
Thank you once again.